Okay, so lecture 14 is going to be a little bit different than usual. Generally, I cover a decent amount of theory, and I give you an example for each of these things. Um, Try to see how you can apply the theory to some geoscience problems. Some of them are obviously simplified. In this lecture, I would like to do some more mathematical problems so that you can get familiar with some of these tools, because matrices and vectors are commonly used in different problems, but not all the students they have the ability to work with matrices and vectors. Um, so we're going to do some basic linear algebra problems and see um, how to apply the tools that we applied, the notions that we applied last time. Um, I think that it's really hard to cover all the linear algebra tools that you might find in inverse theory. So don't hesitate to send me an email and ask me. This is something that I have never seen before, and so on and so forth. I also don't expect you to solve very complicated inverse problems. I would like you to be able to solve a very simple inverse problem. And then if you need additional tools to solve complicated inverse problems in your research, you can always contact me. Okay, so let's start with basic exercises in using matrices and vectors. So let's say that we have, so this is going to be purely a lecture of exercises. We have a matrix A, and the matrix is simply 1, 2, 3, 4, 2, 2, 1, 3, 4, 6, 7, 11. So this matrix is 3 rows and 4 columns. So we want to compute the null space of A. So we said before, well, this is the first question. So we said before that the null space, it's also called the kernel space sometimes. I didn't tell you that last time, I think. Of a matrix A is the set of all the vectors x in Rn such that A times x is equal to 0. Okay. Now, in order to be able to multiply A and x, x has to be a column vector of 4 elements, because we have 4 columns in the matrix A. So in this specific case, n is equal to 4. Okay, so if we do, so A is a matrix 3 by 4, x is going to be a vector x1, x2, x3, and x4. And this one here, so the product of a matrix 3 by 4 times a vector 4 by 1 is going to be a vector 3 by 1. And this one here is going to be the null vector, so there are 3 zeros here. So now we want to find all the possible combinations, x1, x2, x3, x4, or all the vectors x, such that this is true. Sorry, this is, yeah. Okay, so we're going to try to do it. So we have to do ax. So this is, I'm going to just copy the matrix, 1, 2, 3, 4, 2, 2, 1, 3, and 4, 6, 7, 11 times x1, x2, x3, and x4. And we want this quantity here to be equal to 0, 0, and 0. Okay? So essentially, if we remember how the multiplication between a matrix and a vector is, so we take this row here and we multiply by this column here. And we do the dot product, so the result is going to be this number here, the 0 here. Let me change the color so that it's not messy. Okay, so what we do is that the first row is going to be 1 times x1 plus 2 times x2 plus 3 times x3 plus 4 times x4 equal to 0. Okay, now we're going to do it for the second row. So I'm going to use a different color. So we're going to do this row here times this one here, and it's going to be equal to this. So it's 2x1 plus 2x2 plus 1x3 plus 3x4 equals 0. And then the last one is this one here. So the third vector times the x equal to 0. So this is going to be 4x1 plus 6x2 plus 7x3 plus 11x4 equals 0. Okay, so well, these three equations, they have to be solved in a system. So this is a system of equations. We have 3 equations and 4 unknowns. So the system is underdetermined. Okay, there are different ways to solve system of equations in this form. I think that the easier one is by substitution. So we could say that, for example, x1 is equal minus 2x2 minus 3x3 minus 4x4. And then we're going to replace x1 in the second and third expression. So this is 2 times this expression here, minus 2x2 minus 3x3 minus 4x4 plus 2x2 plus x3 plus 3x4 equals 0. And then 4 times minus 2x2 minus 3x3 minus 4x4 plus 6x2 plus 7x3 plus 11x4 equals 0. Okay, so now x1 has already been written in an explicit form, so I'm now going to copy it. Now here we're going to do some simple algebra. It's minus 4x2 minus 6x3 minus 8x4 plus 2x2 plus x3 plus 3x4 equals 0. And this is minus 8x2 minus 12x3 minus 16x4 plus 6x2 plus 7x3 plus 11x4 equals 0. Okay, so again, x1 is exactly the same. Now I'm gonna do the math here. This is minus 2x2, so I sum this one here and this one here. Then there's this one here with this one here, so it's minus 5x3. And then this is minus 8x4 equals 0. Sorry, minus 5. I forgot one element. Okay, and then this is minus 2x2. This is x3, so it's minus 5x3, and then minus 5x4 equals 0. Now these two are the same, so x1 is equal to the expression that we have seen before. And then we can write x2 explicitly. So we change the sign. and then we move x3 and x4 to the right. So this is x2 is equal to, everything is going to be divided by 2. And then I moved x, it's minus 5x3 minus 5x4. So imagine that you're taking this one here to the right. So it's going to be positive. We're going to divide by 2. So it's minus 5x3 divided by 2 minus 5x4 divided by 2. Okay, well, the third one is exactly the same, so there's no point of doing any math here. So we just have two equations. Now, in the first one, we can replace the expression. So it was minus 2x2. So x1 is equal to minus 2x2 is equal to 5x3 plus 5x4 minus 3x3 minus 4x4. And then x2 is something that we have already solved. We just solved for. So I'm not going to copy it. So now x1 is equal to 2x3 plus x4, and x2 is equal to minus 5 divided by 2 x3 minus 5 divided by 2 x4. Okay, so we have I said two equations in 4 unknowns. So at this point we can call, say, x3 equal s and x4 equal t. So we pick a value for these two. So what we get is that, so we said x3 is equal s, x4, x3 is equal s, x4 is equal t. So now x1 is equal to 2s plus t, and x2 is equal to minus 5 divided by 2s minus 5 divided by 2t. Okay, so we have two parameters that we can choose however we want, and then these two for x3 and x4, and these two, they will define x1 and x2. Okay, so we take s equal 1 and t equal 1. Well, sorry, let's take s equal 1 and t equals 0. Then we get the vector 2 minus 5 divided by 2, 1 and 0. So this one here is one of those vectors x, such that a times, so x equal this vector here, a times x is equal to 0. And then if we take s equals 0, t equals 0, t equal 1, then we take x is going to be 1 minus 5 divided by 2, 0, 1. So this is also a vector such that ax is equal to 0. So these two vectors, we can call it x, well, let's call them u and w, just to give them different names. U and v. Okay, u belongs to the null space of A, and v belongs to the null space of A. In general, for all the possible choices of s and t, the vectors that you get will belong to the null space of A. So if you take a vector in the form x equal to 2t plus s minus 5 divided by 2t minus 5 divided by 2s. Sorry, 2s plus t. And then s and t. So these are this is the general expression for the vectors that belongs to the null space of A. Now you have two free parameters, s and t, and then the first two components are determined by the values of s and t. So we can say that the dimension of the null space is equal to. The correct way to write the solution would be that the null space of A is the span, so it's the space generated by the vectors. Well, we take the first one with s equals 0 and t equal 1, s equal 1 and t equals 0, sorry. And then the second one, which is the other one, so it's 1 minus 5 divided by 2, 0, 1. So we say that the null space of A is the subspace generated, span means space generated by these two vectors. Okay. We can write now we want to compute the range of A. Well, first of all, it is useful to compute the dimension of the space. The dimension of the range of A can be computed using the rank nullity theorem. Which says that the dimension of the null space plus the dimension of the range of A, well, let's write it in red since this is a result that I think I didn't cover last time. And again, I don't expect you to know everything about this. So this is a review, and I'm aware that it might include topics that you haven't seen before. If we're going to need those in inverse theory, in the inverse theory part, I'm going to be more detailed about that. So if you already know them, this is going to be a good review. Otherwise, don't worry about it. We're going to cover these topics in details if we need them. I would say that for undergraduates, this is not necessary, and I'm not going to the homework is not going to include anything about that, so I wouldn't worry about it. For grad students or for undergrads who would like to go to grad school, especially in geophysics more than geology, then it's going to be for sure useful at some point. So this theorem says that the dimension of the null space of A plus the dimension of the range of A is equal to n, which is the dimension of the space. It is the number of columns of the matrix A. So A is a matrix n by n. So the dimension of the null space plus the dimension of the range is equal to n. So in our case, in our example, we know that the dimension of the null space is equal to, and we know that n is equal 4. So the dimension of the range of A is equal 4 minus 2 equal 2. Now, the range of A, by definition, is the set of all the possible linear combinations of its column vectors but this one here, it means that it is the space generated by two linearly independent column vectors of A. So we can write the range of A as the span generated by, let's look at A again. So we can take 1, 2, and 4, and 2, 2, and 6. We're going to take two vectors because we know that the dimension of the range of A is equal to, thanks to the theorem that we covered before. And then we can just take two linearly independent column vectors of A, and these are going to be the vectors that generate the range of A. Okay, let's try to do it with a different matrix. Well, we're going to take A transpose. So A transpose simply means that we're going to switch the rows and the columns. So the first row was 1, 2, 3, 4. Now this is going to become the column. So it's 1, 2, 3, 4. The second one is 2, 2, 1, 3. The third one is 4, 6, 7, 11. Now remember that the dimension of the range of A transpose is equal to the dimension of the range of A for any matrix A. So this means that the dimension of the range of A transpose is equal to 2. So we apply the definition of range of a matrix, which is again the set of all possible linear combinations of its column vectors, which means the space generated by two linearly independent column vectors of A. So the range of A transpose is equal to the span of 1, 2, 3, 4 and 2, 2, 1, 3. Okay. Now we want to compute the null space of A transpose. I didn't. Okay. Now we're going to do it by definition again. So this means that we want to find the vectors x such that, like in Rn, where n is the number of columns, so the number of columns of the transpose is not 4 anymore, it's 3. So we want to find x in R3 such that Ax is equal to 0. So we have that 1, 2, 4, 2, 2, 6, 3, 1, 7, and 4, 3, 11. So this is A transpose. Times x1, x2, x3, the vector in R3. This one here is going to be equal to 0, 0, 0, and 0. Because, again, the dimension of this one here is 4 by 3. This one here is 3 by 1, so this one here has to be 4 by 1. And again, we're going to do it by, oh, I can do it this way too, like this. And then we're going to do the second row times the column equal this. And then we're going to do the third row by this one here equal this. And then the fourth times this equal this. So we're going to have again 4 equations. So we do the first one. We have 1, so we do the dot product of this one here times this vector here, and it's going to be equal to this. So this is 1 times x1 plus 2 times x2 plus 4 times x3 equals 0. 2x2 plus 2x2 plus 6x3 equals 0. 3x1, sorry, this one here was x1. 3x1 plus 1x2 plus 7x3 equals 0. And then finally 4x1 plus 3x2 plus 11x3 equals 0. Okay, so we're going to try to solve it. Now, notice that you have 4 equations in 3 unknowns, so this is going to be overdetermined. I think that if you look at it, the fourth equation can be expressed as the fourth one minus the third one minus the first one, but anyway, it doesn't really matter. We can figure it out by substitution. So x1 is going to be equal to, if you want to use Gauss elimination, you can do it if you're familiar with that. So you can do it either by substitution, which is the easiest one, but it could be the longest way. Substitution or Gaussian elimination. Okay. And this is true for all the systems of linear equations. So this one here is the easiest one, the substitution. The Gaussian elimination, well, if you're familiar with that, the solution becomes easier. Elimination. But it might be a little bit tricky sometimes to find the right elimination to do. So we're going to go for the substitution, which means that we explicitly write one variable and we substitute it in the other equations. So this one here would be x1 equal minus 2x2 minus 4x3, and then we're going to substitute it in the second expression, in the second equation. So it's 2 times minus 2x2 minus 4x3 plus 2x2 plus 6x3 equals 0. And then again 3 minus 2x2 minus 4x3 plus x2 plus 7x3 equals 0. And then 4 minus 2x2 minus 4x3 plus 3x2 plus 11x3 equals 0. Okay. So again, I'm now going to copy x1 again. So this one here is minus 4x2 minus 8x3 plus 2x2 plus 6x3 equals 0. This one here is minus 6x2 minus 12x3 plus x2 plus 7x3 equals 0. And then minus 8x2 minus 16x3 plus 3x2 plus 11x3 equals 0. Okay, here we have minus 2x2 minus 2x3 equals 0. Here we have minus 5x2 minus 5x3 equals 0. and then minus 5 again. So it's minus 5x2 minus 5x3 equal to 0. Okay. Well, if we divide by 2 the second equation and we divide by 5 the third one and the fourth one, we get exactly the same results. So these two are redundant. So the first one is x1 equal minus 2x2 minus 4x3. And the second one is simply minus x2 minus x3 equals 0. So we get x1 equal minus 2x2 minus 4x3, and x2 is equal to minus x3. So at this point, x1 is equal minus 2x2, which is plus 2x3, minus 4x3, and x2 is equal to minus x3. So this one here is simply minus 2, well, x1 is equal to minus 2x3, and then x2 is equal to minus x3. Okay, so at this point we have one free parameter, which is x3. So we're going to call x3 equal t. So now x3 is equal t, x2 is minus x3, so it's equal minus t, and x1 is equal minus 2x3, which is minus 2t. So if t is equal 1, we get the vector x equal minus 2, minus 1, 1, which belongs to the null space of A transpose. Okay, so we can say that the null space of A transpose is the space generated by the span of minus 2t minus t 1, or we can take t equal 1, so it's minus 2 minus 1, 1. So the dimension of the null space of A transpose is 1. We can just, if you want to double check, you can apply the theorem as we have seen before. We said that the dimension of the range of A transpose plus, or of the null space of A transpose plus the dimension of the range of A transpose is equal to n. N is the number of columns. The number of columns, so again, number of columns of A transpose, so this is equal 3. So the dimension of the null space is 1 plus the dimension of the range is 2, which is equal to 3. Well, we also said that we can compute the rank of a matrix, the rank of A. Well, this is equal to the dimension of the range of A. Well, let's write it as a result. So the rank of A is equal to the dimension of the range of A. So if you want to compute the rank of A, well, RA is less than or equal to the minimum between m and n, so which is equal to 3. So the rank of A has to be greater than or equal to 3. Well, the way we can do it is that I'm going to write A here again so that we don't have to go to move the screen up and down. So we said A is equal to 1, 2, 3, 4, 2, 2, 1, 3, 4, 6, 7, 11. Okay. Well, we can use the rule of the determinant of the submatrices. So we know that the determinant has to be less, that the rank has to be less than or equal to 3. So we can look at all the possible submatrices of size 3 by 3. Well, we only have 4 possible options. One is this one here. One is this one here. And then we can take, well, this is going to be hard to show. Let's see. We're going to have these 2 columns and this one here. Or we're going to have, running out of colors here. Or we're going to have this one here and this 2. So I'm going to write them down for simplicity. So we have the determinant of 1, 2, 3, 2, 2, 1, 4, 6, 7. We have determinant of 2, 3, 4, 2, 1, 3, 6, 7, 11. We have the determinant of 1, 2, 4, 2, 2, 3, 4, 6, 11. And we have the determinant of 1, 3, 4, 2, 1, 3, 4, 7, 11. So these are just all the submatrices of dimension 3 by 3. So the first one is the first 3 columns. I'm looking at submatrices 3 by 3 because I know that the rank of A is less than or equal to the minimum between the number of columns and the number of rows. So it has to be 3. So I look at all the possible submatrices. We only have 4 rows, so we have 3 rows and 4 columns. So we have only 4 options. We take the first 3 columns, we take the last 3 columns, we take the first column, the third one, and the fourth one, and we take the first column, the second one, and the fourth one. So these are the 4 submatrices that we obtain. Now, I did the math for you, and so this one here is equal to 0, this one here is equal to 0, this one here is equal to 0, and this one here is equal to 0. So we know for sure that the rank of A has to be less than or equal to 2. It cannot be 3, because if it was 3, there would be at least one that was not 0. Okay, so I'm going to rewrite the matrix here one more time. This is going to be the last one. So we have 1, 2, 3, and 4, 2, 2, 1, and 3, and 4, 6, 7, and 11. Okay, so now we're going to work with submatrices 2 by 2. Well, we're just going to look at the first one because that's going to be enough. As long as we get one determinant that is not 0, that's the rank. So we're going to look at this one here. Well, for a 2 by 2, the determinant is easy to compute. So this one here is the determinant 1, 2, 2, 2. So this is the product of the main diagonal minus the product of the second diagonal, the opposite of the diagonal. So this is going to be minus 2, which is not equal to 0. So this implies that the rank of A is equal to 2, because we found a submatrix which is whose determinant is not equal to 0. And we know that the range of A is equal to the dimension of the rank of A is equal to the dimension of the range of A, which is equal to 2. Now, we could have the dimension of the range of A is equal to the rank of A, which is equal to 2. So we computed the dimension of the range of A in two different ways, using the range, using the rank of the matrix, or using this theorem that I gave you before. We computed the dimension of the null space first, and then we computed the dimension of the range using this theorem here. So if you can't compute the dimension of, if you don't know how to compute the dimension of the null space of A, I write not known, which means that, or that you don't know how to compute it, then you can use the theorem, the dimension of the null space of A plus the dimension of the range of A is equal to n. This one here is equal to the rank of A. Computing the rank means basically looking at the determinants of the submatrices and finding one which is not 0. So in this case, we could say the dimension of n of A is equal to n minus r of A, which is 4 minus 2, which is equal to 2. And for the, we know that the rank of A is equal to the rank of A transpose, which means that the dimension of the range of A is equal to the dimension of the range of A transpose. So if we want to compute the dimension of the null space of A transpose, we can say that this is equal to n minus, sorry, m, because the number, the dimension n in the theorem, this one here, is the number of columns of the matrix. The number of columns of A transpose means the number, so this is the number of columns of A transpose, which is the number of rows of A by definition, minus the dimension of the range of A transpose. So this one here is 3 minus 2, which is equal to 1, which is exactly what we found. Well, a smart trick to find the rank of A, so we wanted to find that the rank of A is equal to 2, so I had to go through all these calculations to show that it was not 3, so it had to be less than or equal to 2, so we found the determinant. I couldn't start from this point because we know that the range is less than or equal to 3 in this specific case. So finding that the determinant of 1, 2, 2, 2 is different than 0 means that it's at least 2, but we don't know if it is 3 or not. We have to do all these calculations to show that all the determinants are 0 to compute the, to prove that the range is less than or equal to 2, and then this one here proves that it is 2. There would be an alternative way. If you look at the matrix again, I'm sorry to write it down several times, but I think that if I keep flipping up and down, the screen is going to be even worse. Okay, if you look at the second, at the third row, this one here, so I'm going to call this one here R3 as a vector, this one here R2, so I can write it as like this. So R1 is a vector, R1 is 1, 2, 3, 4. R2 is 2, 2, 1, 3. And R3 is 4, 6, 7, 11. So if I put these three vectors together, I get a matrix. Well, if you look at R3, R3 can be expressed as a linear combination of R1 and R2. Indeed, R3 is equal to 2 R1 plus R2. If I take the double of R1, so the double of R1 is, I'm going to write it as a column just to make it easier, but plus R2, which is 2, 2, 1, 3. I'm terrible with brackets. Okay, if you do the math here, you get 2 times 1, 2, plus 2, 4, 2 times 2, 4, plus 2, 6, 2 times 3, 6, plus 1, 7, 2 times 4, 8, plus 3, 11, which is exactly equal, this is R3, this is 2R1 plus R2. So it means that R3 is a linear combination of R2 and R1. So the rank cannot be 3 because out of 3 rows, one can be computed as a linear combination of the other 2. So it means that the rank has to be less than or equal to 2. And then you can simply, R1 and R2 are linearly independent. So this one here leads to the fact that the rank has to be strictly less than 3. And then R1 and R2 are linearly independent. Well, indeed, R1 is not equal to a constant alpha times 2. Because if you take, no matter what alpha you take, if you take alpha equal 1, then alpha has to be, if you take alpha equal 2, then the first element 1 times 2 is 2, but 2 times 2 is 4. So these two are not going to be, cannot be expressed as a linear combination. So this one here concludes that the rank of A is equal to. So that's an alternative way to compute the rank of the matrix. Okay. Let's say now that we have a generic matrix, A. Well, this is a different exercise. So here I simply try to review different rules that we can use to compute the dimension of the null space, the dimension of the range, the rank of the matrix, and so on and so forth. So these rules, they apply in any general case. So let's say that we have a matrix A which is 9 times 6. Okay, so A can be written as, we don't know the values in this case, but A can be written as A11. We have 9 rows, so this is going to be A91. We have 6 columns, so this is A61, and this is A96. Okay. Let's say that we know the dimension of the null space of A is equal to 5. And we want to compute the rank of A and the rank of A transpose. Well, again, we know that the dimension of the null space of A plus the dimension of the range of A is equal to n, where n is the number of columns. So it means that the dimension of the range of A is equal to n minus the dimension of the null space of A. The null space of A is given, so this is the number of columns, 6 minus 5, which is equal to 1. So the rank of A is equal to 1. And we know that the rank of A transpose is equal to the rank of A, which is equal to 1, too. Okay, so we also covered the definitions of norms. So if we have a vector space V, so the norm, so this dot here means that you can take any element in V, okay? The norm is a function that's associated to any vector in V, a real number. So the norm of V, you take a vector V and you associate the norm of V. And it must have the following properties. Well, if you want, you can, if you don't like this notation here, you can simply write the norm. So the norm is a function from V to the set of real numbers such that you take a vector V in V and you compute the norm of V. And it must have these following properties. The norm of V is greater than or equal to 0. The norm of V is equal to 0 if and only if V is the null vector for every V in the set of real numbers. In the vector space V. So if you take a vector and its norm is equal to 0, then V is the null vector. And the norm of the null vector is 0. Then the norm of alpha V is equal to the absolute value of alpha times the norm of V for every alpha in the set of real numbers and for every V as a vector V. And then if you take the norm V plus W is less than or equal to the norm of V plus the norm of W. This is also called the triangular inequality. And this is valid for all the V and W in V. So for example, if we take V equal R2, so the usual Euclidean plane, then the norm in L2 can be, for example, the Euclidean norm, which is the square root of the absolute value of x1 squared plus the absolute value of x2 squared, where x1 and x2 are the coordinate of x. This doesn't have to be necessarily a multidimensional space of like Rn. It can be a space of functions. So for example, V could be the space L2 on the interval AB. Well, this one here is the space of square integrable functions in A, B. And you can define the norm of a function as the integral, the square root of the integral between A and B of the square of f of x for every function in this space here. So you take all the functions that can be integrated, whose square can be integrated over the interval A and B, and the norm is going to be the integral, the square root of the integral of the square of the function. Now notice that the norm is not linear. If it was linear, what is the linearity means? That if you take g of x plus y, this is equal to g of x plus g of y. Well, this is not the case because we have the triangular inequality. The norm of, say, x plus y is less than the norm of x plus the norm of y for x and y in R2. So let's say that we define a function, say f1, that goes from the interval minus 1, 1 in R. And f1 of x is equal to a constant value 1 divided by 2. Now we can define the norm 1 of the function f. Well, let's call it, instead of f1, it might be confusing, so let's call it just f. The norm 1 is simply equal to the integral between minus 1 and 1 of the absolute value of f of x in the x. So this is the integral between minus 1 and 1 of 1 divided by 2 in the x, which is 1 divided by 2 of x between minus 1 and 1, which is, well, it's 1 divided by 2 minus plus 1 divided by 2, which is equal to 1. If you take the norm L2, the integral between minus 1 and 1 of f of x square in the x, well, this one here is the square root of the integral between minus 1 and 1 of 1 divided by 4, the square of 1 divided by 2, which is 1 divided by 4 square root of x between minus 1 and 1, which is the square root of 1 divided by 2, which is the square root of 2 divided by 2. You can also define the norm infinity, which is the maximum of the absolute value of the function for x that is in the interval minus 1, 1. Well, this is a constant, so it's equal 1 divided by 2. Now, if you take a function g of x, so g that is defined, let's say that we are on the same interval, minus 1, 1 in R, and we define g of x equal 2 divided by the square root of 5, so this is a constant, times x. Well, now the norm of g, the norm 1, will be the integral between minus 1 and 1 of g of x in the x, which is equal to the integral between minus 1 and 1 of 2 divided by the square root of 5 x in the x. This is a symmetric function, so it can be written as 4, so it would be 2 times 2 divided by the square root of 5, the integral between 0 and 1, so we take only the positive part and we multiply it by 2 of the absolute value of x in the x. And then this is 4 divided by the square root of 5 times x2 divided by 2 between 0 and 1, and this one here is 2 divided by the square root of 5. If you take the L2 norm, this is the square root of minus 1, 1, the integral between minus 1 and 1 of the absolute value of g of x squared in dx, which is we're going to solve it again as we did before. So we're going to take the square, which is 4 divided by 5, and multiply by 2. So this is 4 times 2 times 4 divided by 5, the integral between 0 and 1 of the absolute value of x squared in dx. So this is a divided by 5, x cubed divided by 3 between 0 and 1 under square root. So this is the square root of 8 divided by 5 times 1 divided by 3, which is 8 divided by 15 minus 0, which is 2 times the square root of 30 divided by 15. And then again, if you take the infinity norm, this is the maximum between minus 1 and 1 of the absolute value of g of x. Well, this function is 2 divided by square root of 5 times x. The maximum is going to be 1, so it's going to be in 1, so the maximum is going to be equal to 2 times divided by the square root of 5 times 1. And finally, we're going to look at a function, let's call it h. We're still going to be defined over 1, the interval minus 1, 1, and h of x is equal to minus x squared. Now, the norm 1 of this function is going to be the integral between minus 1 and 1 of h of x, absolute value in dx, which is equal to 2 times the integral between 0 and 1 of the absolute value of x squared, which is 2 times x cubed divided by 3 in 0 and 1, which is 2 divided by 3. The norm L2 is going to be the square root of the integral between minus 1 and 1 of the absolute value of h of x squared in dx, which is equal to twice the integral between 0 and 1 of the absolute value of x squared in dx under square root. So this is 2 times x power 5 divided by 5 between 0 and 1 under square root, which is the square root of 2 divided by 5 times 1 minus 0, which is the square root of 10 divided by 5. Square root of 10. And then we have the norm infinity, which is going to be the max of x that belongs to minus 1, 1 of the absolute value of h of x, which is equal to 1, because the maximum is in 1. Okay, so these are typical problems that we see in linear algebra: computing norms, computing dot products, computing ranks and dimensions of matrices and dimensions of null spaces and ranges. We're not going to necessarily use all these tools in the class, and some of you might be familiar with some of them and not with others. Again, don't worry about if you didn't understand part of this. We're going to look at every time we cover a topic in inverse theory, we're going to look at the details of the linear algebra tools that you need. But in case you want to go to grad school, this is something that you're supposed to know, especially for geophysics. For geology, probably most likely it's not required unless you do something more computational in the field. Okay, so this is pretty much what I wanted to cover today. So next time I'm going to introduce the concept of inverse problem.